finally resolved later this last year. Let me explain what the problem is, and then so problem is very easy to define. It says that you have one machine, okay, and you're given a set of n jobs, okay, and each job you're specified three things. Each job has a release date. Release date basically means that you can only start processing this job from this time onwards. Okay, so the release date is 5, then it means that you can only start processing this job from time 5 onwards. Okay. Each job has a certain size, which is Pj. So, and it has a certain weight, which basically says how important this job is. Okay. And all of this information is given to you, and the only job is now to sort of build a schedule. Okay. Specify at each point of time which job will be processed, okay, so that you want to finish all the jobs. Okay. So that is the problem statement. Let me say one more thing. You are allowed to preempt a job, which basically means that you can do a job for a while, then you stop it, do something else, and then you can bring this back. Okay. So for example, so this picture is basically saying that this job has release date here, okay, and this is the size of this job, okay, and I'm not specifying the weights. It doesn't right now. Okay, and the schedule could look like this. Okay. So basically, you can only start this red job at this time. And you can do this red job for a while and then bring in the yellow job and maybe bringing this job here and then do the remaining part of the red job here, and so on and so forth. Okay. So, alright, and what are we interested in? We are interested in what is called the flow time of a job. Okay. So, flow time of a job is essentially the amount of time it spends in the system. Okay. So, think of this job arriving at this time. Okay, this red job arrives at this time, and there's a mistake, I guess. It finishes at this point of time. So it's the difference between the time at which it finishes minus the time at which it arrives. Okay. And so this is called the flow time of a job. And all you want to do is you want to minimize the total sort of weighted flow time. So jobs which have higher weight, they should have smaller total sort of amount of time they spend in the system. Okay. All right. So so find a schedule which minimizes the total weighted flow time, and this problem is, again, it's a very old problem, goes back a few decades, and it's known to be NP hard. Okay, so you cannot solve this problem in polynomial time. And so in this talk, what we are interested in is approximation algorithm, which basically means that I want to give an efficient algorithm, and for this algorithm I want to measure what is called the approximation ratio, which says that I want to design an algorithm and I want to compare it with the optimal algorithm. Okay, and this ratio will be bigger than 1, and I want to have an algorithm for which this ratio is as small as possible. Okay. All right. So let me just go over what is known about this problem. So let's start with some special cases. So the simplest case is, let's say all the weights are 1. So in this case, we teach this in undergraduate algorithms, that a very simple algorithm called shortest remaining processing time, SRPT, turns out to be optimal. Okay, so let me explain what this algorithm is. It basically says that at any point of time, you look at all the jobs that are remaining, and you take the job for which the remaining time is as small as possible. Okay, you schedule that job next. Okay. So for example, let's say at time 0 this job is there. So you just schedule this job for 1 unit of time, and at next point of time maybe another job arrives, this red job. Now the red job has only 1 unit of time remaining, while the blue job has 2 units of time remaining. So you prefer the red job, so you do the red job now. And then another yellow job arrives, which is even longer. So you go back and do the blue job because it has only 2 units remaining, and so on and so forth. Okay. And it's a simple greedy algorithm, and it's not difficult to show that this is optimal. Okay. The other special case is when this is called the stretch metric, when the weight of a job is inversely proportional to its size. Okay. So basically it says that if you are a short job, you have very high priority. If you are a long job, then your weight is small. In this case also it is known that the same algorithm is a 2 approximation algorithm, which basically means that whatever is the optimal solution, this simple algorithm will be within a 2 approximation, 2 factor of that. Moreover, for this problem, we also know a PTAS. PTAS basically means that you can specify any constant bigger than 1, let's say 1.001, and there is an algorithm which is polynomial time. The running time of that algorithm will get worse as this constant becomes closer to 1, but for any fixed constant above 1, there is a polynomial time algorithm for that, okay, with that approximation ratio. Okay, so these are the special cases. For the general case, there has been a lot of work on this problem. The ones which are sort of colored blue, they are what is called online algorithms, which basically means that I don't even have to reveal all the input to you. Okay, so as you go along, these jobs will keep on arriving. Okay, but in this talk, we're only going to look at offline algorithms, but just wanted to point out that some of these are also online. Okay, so the first sort of non-trivial results were like approximation ratios which were of the order of like log square p. So there are 2 parameters which are of interest here. P denotes the ratio between the largest to the smallest size of a job, and W denotes the ratio of the maximum to the minimum weight of a job. Okay, so what is known is people know like approximation algorithms which are about, the approximation ratios are somewhat logarithmic in P or W. Also, approximation algorithms are known where you can get as close to 1 as you want, but the running time is not really polynomial. It's something of the like n to the order log P log W. Okay, so it's not a truly polynomial time algorithm. Then in 2010, Bansal and Proust came up with a nice idea, and they gave approximation algorithms where the approximation ratio was of log log NP. So till this point, we only knew logarithmic approximation algorithms. This was the first result which gave a sort of a log log result. And our result is basically we give a polynomial time algorithm, but it is polynomial in n, okay, and P and W. Okay, and its approximation ratio is a constant. So this is not a truly polynomial time because it's possible that P and W could be exponential, but assuming that P and W are polynomially bounded, this is the first constant factor approximation algorithm for this problem. And I'll say a bit about what is so what subsequent work has happened on this problem later. Okay, so in this talk I will sort of give you some idea about how this result is. Sure. Sorry? Yeah, that's a good point. So I was going to say that it's because of this result, it is possible that there is a p-test for this problem. That is not ruled out.
What's the order? So what's the constant?
Yeah, yeah, I don't know, somewhere around 100 or something. Okay, so so here's the plan for the rest of the talk. So I will describe what is called an integer program. So this is a standard sort of tool for which people use in approximation algorithms, that they start with an optimization problem and they specify an integer program for that. Okay, so integer program is essentially like a linear program, but all your variables are supposed to be either 0 or 1. And I mean, this integer program, people have used other integer programs, but we'll introduce a new one. And we'll show that this integer program, you can relate this to a graph theoretic problem on trees. So this graph theoretic problem will look like what is called multi-cut problem. I'll describe what this is. And again, we don't know a constant factor approximation for this problem, but what we will show is that the kind of instances that you get for multi-cut problem, those instances can be handled using dynamic programming. Okay, so that will eventually result in the result. Okay. Okay, so let me describe the integer program. Okay, so remember, so in integer program, what we have to do is we have to write down variables which are going to be either 0 or 1, and express all the constraints and the objective function in terms of these 0, 1 variables. Okay, so I'll have only these variables. Okay, so I'll have variable x, j, t. These are the only variables I'll use, and j is a job and t is a time. Okay, think of t as being integer times only, doesn't matter. Okay. And the meaning of this variable would be that xjt is going to be 1 if this job j is unfinished at time t. Okay. So if it, I'll use the word alive, which basically means that it completes after time t. And if job j has finished by time t, I'll make it 0. Okay. So this is the, these are the only variables I'll use. So so let's see how we can write down the flow time of a job j. Okay. Remember, what is the weighted flow time of a job j? It's weight times the amount of time it spends in the system. Okay. And that I claim can be written like this. Right. Look at every time after its release date and look at the value of xjt. If you add up this thing, it's exactly equal to the amount of time it's going to spend in the system. Right. So my job is to minimize the sum over all jobs of this quantity. Right. So this is my objective function. Okay. So I've written down my objective function as some sort of linear function of xjt variables. Okay. Okay. All right. Now that's fine, but now I have to somehow express the fact that xjt corresponds to a schedule, right? So xjt cannot be just arbitrary 0, 1 variables; they have to correspond to some sort of schedule. Okay. So here's what I'm going to write. Okay, I'll say that look at any interval, okay, any time interval st, and look at all the jobs which are released during this interval. Okay. And if the total processing time of these jobs is much more than the length of this interval, some of the jobs must be alive beyond time t, right? You cannot finish all these jobs in this segment if the total length of these jobs is more than the length of st, right? So, okay, so look at all the jobs which are released during this interval. Okay, there could be, these are the jobs, and look at their total processing time. Okay. And the claim is that this condition must be satisfied. Okay. So let's see what this condition is saying. Okay. This condition is saying that look at all the jobs which finish after time t. Okay. The total size of all of these jobs must be more than this difference here. Okay. So what is the right hand side? Right hand side is look at all the jobs which are released here, add up all their sizes. Okay. This is the total amount of processing you have to do over these jobs. Okay. And the total amount you can do inside this interval is only the length of the interval. Okay. So the total amount of processing that has to happen after time t must be at least this much. Okay. And that's all this saying. Okay. So there's some sort of packing or covering kind of constraint, right? It's saying that look, lot of jobs are getting released here, so if this segment is not long enough, then a lot of them have to be transferred here. Not everything can finish here. Okay. So I'm just writing a linear condition which captures this. Okay. So this is my integer program, right? This is the objective function. This is the constraint I wrote down for every interval. For every interval. This is kind of obvious. It says that if you're alive at time t, then you must be alive at time t minus 1 also. Right? If you're, and your xjt is either 0 or 1. Okay. Okay. So this is the complete description of the same problem in terms of these xjt variables. And all I've shown to you is that if xjt are what they're supposed to mean, then all of these conditions must be satisfied, and this exactly captures my objective function. Okay, so okay, and the converse is also true. It's something I will not prove here, that if I give you a solution to this integer program, then I can build a solution, a schedule out of it. Okay. So essentially this is exactly the problem that I'm trying to solve. Okay. Now it turns out that these conditions are kind of nice. They are called, in the literature, they are called covering constraints. Okay. Basically you have some sort of linear function of the x variables, and you want this linear function to be at least some quantity here. Okay. So these are called covering conditions, and if this was not there, this will look like what is called a covering integer program. Okay. And these are very well understood, but these are kind of annoying constraints. Okay. So these are the problematic constraints, because this introduces some sort of dependencies across different variables. If these were not there, these will look, xjt's will look like completely independent variables. There will be no dependencies across them. Okay, but that's hard to imagine, because then if these were independent, then this could lead to meaningless things, right? It could say that job j is alive at time 5, but not alive at time 3, which is kind of absurd. Okay, so you need these kind of conditions. Okay, all right. So what I will show you is that you can actually get rid of this at the expense of some loss in approximation ratio. Okay, and this is the standard trick that people use in lot of these settings. So let me show you what that is. Okay, so I want to get rid of these conditions. Okay, so I'm going to write a different program now. Okay, and the way this is going to work is the following. Okay, so think of a job j which is getting released at this time. Okay, now remember, my objective function is going to say that, I'm going to measure for how long it is going to be alive in the system. Okay, but I'm going to simplify this notion. I'm going to say that let's put some markers. Okay, let's put a marker at length 1 from its release date, at length 2 from its release date, at length 4 from its release date, and so on. Okay, so let's have some markers of exponentially increasing length. Okay, 1, 2, 4, 8, and so on. And if a job is going to sort of, let's say, finish processing here, I'm going to assume that it actually finishes here. Okay, it will only lead to twice increase in the flow time of the job, because if you are going to be finishing here, you're going to pay this much for your waiting time. I might as well make it finish here. Okay, so this is where you lose a factor of 2 in the approximation ratio. Okay, but what it does for you is that you don't have a variable xjt for every point of time. You only have variable xj1, xj2, xj4, and so on, which basically says that was this job alive till this point or not, was this job alive till this point of time or not. Okay, so it seems like we have saved some variables here, right? Earlier I had xjt, but now only I have these variables for these markers here. Okay, so this is what I will call j comma s. Think of s as a segment like this. Okay, and so as I said, let's say this job j, suppose in the schedule you process this job at these points of time, job j finishes here. I'm going to assume that it actually finishes here. Okay, and so I'm going to set xj1 to be true, xj2 to be true, xj4 to be true, and xj8 would be false. Okay, so S denotes a segment. It would be this or this and so on. Okay, so j comma s just denotes a segment of length 2 to the k for some k. Okay, all right. So I now have variables y j comma s, which says that it is 1 if job j is alive at this segment s. Okay, 0 otherwise. Yeah, so segments, let's say are of exponential lengths. No, they start like this. Okay. They start one after the other. Not from, it doesn't really matter for this, but let's say it starts like this. Okay, so 1 and then 2 and then 4 and one after the other. Yeah, so if you measure from here, this will be like 1 plus 2, 1 plus 2 plus 4 and so on.
RJ is 0. RJ, sorry, 0 is at RJ.
Yeah, 0 is at RJ.
A different job, the 0
Different jobs, yeah, that will be critical for.
then the S is going to synchronize.
Yeah, I will come to that. Yeah, okay. So, but let's write it like this. Okay, so yjs is 1, right, if job j is alive at the end of s, otherwise it is 0. Okay, so all I have done is just saved some variables. That's all I have done so far. Okay, and now I can again express my objective function. I can say that over all such segments, you add up yjs, and then here I used to have weight of job j, but now I will have weight of job j times the length of this segment, because if a job j is going to be alive throughout this, you should be counting wj at each point of time here. Okay, so that's why you're multiplying wj with the length of the segment. Okay, okay, so that let's write the whole thing again. You basically this is your objective function. You have the same constraint. Earlier you had an xjt here. Now I will have the yjs here for that segment s, which sort of goes through this time. Okay, so nothing changes. Again, you have the same xjt less than, right? If a job j is alive at during a segment s and s prime sort of precedes s, it better be alive at s prime also, and so. Okay, so essentially nothing has happened. But one nice thing comes out of this, I claim, is that you can now kind of get rid of this condition. Okay, which basically says that I will be in this absurd situation where job J would not be alive here. It will say that job J has finished here, but then subsequently it will say that you are finishing here, or you are alive throughout this period. Okay, but if you think about it, it's not a worry, because if job J is alive throughout this period of time, you're anyway going to pay 4 units for this job J. Might as well pay a bit more. Okay, so this is one thing I buy from this, right? I can get rid of this thing. Okay, so this notion of dependencies across XJT variable goes away here. Okay, so there's a very standard trick people use. Okay, any questions here? Okay, so this now becomes like a covering IP. Here, yeah, so it's exactly the same thing. So let's look at all the jobs which are released during this period. Okay, let's say J1 is such a job. Okay, and for J1 I have exponentially increasing segments. So I will have that Y variable which contains this time t. So earlier I used to have XJT here, now I will have one of the YJs. Okay, so essentially the same thing, but right. Okay, so this is exactly the so let's look at 2 different jobs. This is one job, this is another job. Okay, and so for this job I will have segments of exponentially increasing length. For some other job I will have similar segments, but the starting points will be different. Right, the starting points will be the release dates. Okay, because you are counting for this job starting from its release date. Okay. And so their segments could, they will look, they'll sort of cross each other. Okay, so for example, this blue segment here crosses 2 red segments. Now what you want is something slightly stronger. What I want is that I want these segments to be what is called laminar. Okay, I don't want them to sort of cross each other. Okay, so for example, I don't want such a picture here. Okay, where this red and this blue segment are sort of crossing each other. Okay, I want that any 2 segments for different jobs should either be contained in one another or be equal to one another. Okay, so this is one technical aspect I need. Okay, so again I'll show you a trick where using which you can do this. Okay, right. So here is the trick. Okay, so first of all I'll do is I'll start. This is the timeline. Okay, right now there are no jobs. Okay, and I'm going to build define several sort of intervals. Okay, so at the highest level I will divide this timeline into 2 equal parts. Okay, then each of these I will divide into 2 equal parts, and so on and so forth. Okay, so all I have done is I have defined several dyadic intervals. Okay, here they are of length, if this length was 2 to the k, this will be 2 to the k minus 1, everything here will be of length 2 to the k minus 2, and so on. Okay, so these are exponentially decreasing intervals. But the nice thing is that they are nested. Okay, and now what I want to do is that those segments that I was defining for those jobs, I want those to be picked from this set only, this collection only, because this collection is nice because no 2 segments here sort of cross each other, because that's how I have defined these things. Okay, so let me show you an example. So let's say job J is released here. Okay, so remember initially I have to define a segment of length 1. So this is the length 1 segment. Now I have to choose a segment of length 2. Luckily there is a segment of length 2 that I can choose here. Okay, now I have to choose a segment of length 4. Luckily there is a segment of length 4. I choose this. Okay, now let me show you another example where I'm not so lucky. Let's say that okay, so let's say a job J is released here. Okay, so initially again I pick a segment of length 1. Now at this point I want to pick a segment of length 2. I see that there is a segment of length 2 available, I pick that. At this moment I want to pick a segment of length 4, but notice that there is no segment of length 4 starting at this point. Okay, so I will continue to pick the same length 2 segment here. Okay, at this moment I see that I can pick a segment of length 4, so I pick a segment of length 4. Now again at this point I don't have access to a segment of this size, so I will just continue with whatever size I have. Okay, so what happens now is that the segments are not really geometrically increasing in length. So the algorithm is very simple, right? You start wherever your release date is, you keep on picking the longest interval at the next level that you can get, right? So you start with length 1, then if you can get a length 2, then good, otherwise just continue on length 1. The moment you can get length 2, you just go up and pick a length 2 interval, and so on and so forth. Okay? So, what goes wrong is that these are not exponentially increasing. Why is that a worry? If they were not exponentially increasing, then remember we said that my integer program can say that this y variable is 1, everything else is 0. So, this length has to account for the length for the entire duration. Okay? So, similarly, this is another example and so on. But what you can show is, okay, so this is the algorithm, right? If possible, move to the next level, otherwise just take the segment in the same level. Okay? Now, here are things that you can prove, okay, and these are the nice things which come out of this, that for any job j, you will, it's easy to show that you will pick the same size at most twice. So, it cannot just keep on happening. It will not just keep on happening that you will just keep on picking length 1 interval. At some point you will, after at most 2 steps, you will go up next to a length 2 interval. Okay? So, even though they are not strictly increasing, it's almost increasing. Okay? So, that takes care of the first issue. The other issue is that if you look at 2 jobs, let's say you pick blue job and black job here. Blue job is released before black job. And if you look at any point of time, then the interval for the blue job will always be containing the interval for the black job. Okay, so if you look at this point of time, this interval contains this interval, contains this interval, contains this interval. Okay, so they are ordered by the release dates. Okay, so why is all this useful? The reason why all this is useful is I can put a tree structure over these segments. Okay. So what I can do is look for the jobs I have defined these exponentially increasing segments, and I can, because they are laminar, I can put a tree structure over them, right? So let's see why. Okay, so just to give you a feel for this, let's say, you know, for each segment that I have defined, I will have a vertex, okay, and if one segment contains another segment, I'll just make it a child of that. Okay, so think of 4 jobs, and these are the segments for these jobs. Okay, so then I will make, you know, V2 and V3 as children of V1. Okay, so whatever laminar structure I have got here, I can put a tree structure on that. Okay, this just follows from the laminar structure here. Okay, fine. And what does this constraint say here now? Okay. So what's the meaning of this constraint? If you just translate what this constraint is saying, this constraint is saying that look at all the jobs which are released here, right? And look at all the segments S which cross this time t, right? Their pj times this y variable must be at least this thing. Okay, but if you look at this picture here, let's look at this time t here. Okay, which are the segments which cross this time t? There is v1, there is v2, and there is v5. And in this tree, it will correspond to a path. Okay. Okay. So here is a different problem. Okay. So I claim that you can translate this, you know, scheduling problem to the following kind of problem on a tree. Okay. So the problem is as follows: I give you a tree. Okay, and in this tree, each of these constraints specifies a path. Okay, so you are given a bunch of paths in this tree. Okay, and what you want to do is you want to, okay, what is yjs here? These variables correspond to vertices in this tree, right? For each segment, I had a vertex here. So what you want to do is you want to pick some of these vertices in this tree. Okay, such that if you look at any path in this tree, look at the total set of vertices that you pick in this path P. Okay, their total pj value of these vertices must be at least some quantity on the right hand side. Okay, so let me define this tree covering problem. Okay, so the problem is as follows. Again, to just repeat that, you are given a tree T where each vertex V has a cost and a size. Okay, so think of cost of a vertex V as its weight, and size as the pj value of that vertex. Okay, and you are given a set of paths in this tree. Okay, so let's say, you know, every path is like an ancestor descendant path, and each path has a demand. Let's denote it by dp. Okay, So this is the instance. How does it correspond to our scheduling problem? Well, for each constraint that we wrote down, I got a path. Okay, and what are the values of these dp? These dp are essentially just the right hand side of these constraints, whatever these things are. Okay, so and what are the vertices of this tree? The vertices of these trees, this tree are exactly the segments here. Okay, so when you're setting yjs equal to 1, you're essentially picking that vertex. Okay, so this is the sort of reformulation. It just says that I give you a tree, every vertex has a cost and a size, and I give you a bunch of paths in this tree. Okay, and the solution has to specify which vertices to pick here. Okay, and you want to pick a min cost subset of vertices such that every path is satisfied. What does satisfied mean? Satisfied basically means that look at, let's say, the green path and look at the vertices that you have picked in this green path. Their total size must be at least the demand of this path. Okay, right, and there's a standard trick by which I can just replace the vertices by edges. Okay, and what I have shown to you is that an alpha approximation algorithm for this tree covering problem will imply an order alpha approximation for the weighted flow time problem. Okay, so this is the first sort of part of the work, which basically says that you can replace this scheduling problem by some sort of problem which is like a tree covering problem. Okay. When all the sort of quantities are 1, when the demand is 1, when the sizes are 1, this is also called the multi-cut problem on trees. Okay, it's well studied. Okay, and so this is, we call this demand multi-cut problem. Okay, let me just tell you what is known about this problem. Again, the same, you can also write a linear program for this demand multi-cut problem, which basically says that this is a variable which says that are you going to pick this vertex or edge or not. And all I've done is just rephrased my requirement. I've said that for every path P, look at all the edges that you have picked and look at their total size. That must be at least the demand of this path P. Okay. So this kind of integer program, they come under the class of what is called column restricted covering IP. And what is known is that using known techniques, you can get a log P approximation for this kind of integer program. Okay, so this is one way of proving a log P approximation here. We don't know what is the integrality gap of this linear program. We believe it is a constant. Okay. So this is the main result that we have, which says that if you give me an instance like this, I can give you a constant factor approximation algorithm, but the running time of this algorithm would be polynomial in n, the number of nodes. It's exponential in the height of the tree. Okay, so h denotes the height of the tree if I shortcut all degree 2 vertices. Okay, so it's polynomial in 2 to the h, and some quantity which is the ratio of the densities of the vertices. Okay, density is basically the ratio of cost and size. For us, it so happens that 2 to the h is exactly the quantity p. Okay, so it becomes polynomial in n and p. Okay, but essentially our algorithm is a dp based algorithm which is polynomial in n and exponential in the height of the tree. Okay, so it is an open problem to come up with a constant factor here, a true constant factor here. We don't know how to do that. Okay, but just so a direct corollary of this result is that the algorithm is polynomial in n and p, and the reason why this is 2 to the h is like p is because what are these vertices in our problem? These vertices correspond to intervals of some size 2 to the k, and when you have, let's say, 2 children of this vertex, these are again 2 intervals of some size 2 to the I, which are nested within this interval of length 2 to the k. So if they are nested, it means that these vertices are corresponding to intervals of length which are one factor less than the size of this interval. Okay, so you can have such branchings only logarithmic number of times. Okay, so that's why this 2 to the h behaves like p. Okay, so I have 2-3 minutes. Okay, so let me just say what is known about one special case. Even the case when this tree is a line is a non-trivial problem. Okay, so let's say the problem was the following, that I give you a line, okay, and every edge has a size, and I give you a bunch of paths in this line. Okay, and all you want to do is to pick a subset of edges here, such that every path is satisfied. By satisfied, it means that whatever is the demand of this path, you have picked at least those many edges. Okay, even this problem is non-trivial, but it so turns out that based on known techniques, Chan et al., you can give a constant factor approximation here. But even this special case is non-trivial. Okay, so I will not get into the algorithm here. Basically, it uses techniques based on dynamic programming. So I'll just skip all this and just come to the last slide. So I'll just skip all this. So let me just talk about what further work has happened on this problem. So Feige, Kulkarni and Lee used our result as a black box to give a truly polynomial time approximation algorithm. So their algorithm runs in time which is polynomial in n and log p. Okay. So it is a polynomial time algorithm. One thing is that our constants are bigger. The reason where we lose constants is that in this translation to this tree problem, we already lose a factor of 8. And then during the dynamic program, we have to round things to powers of, let's say, 16. Okay, we have to ensure that. So one of the reasons why flow time is such a difficult metric is that if I change the size of any job even slightly, the objective function can change a lot. Okay. However, I am free to choose the change the weights of jobs, because they don't affect the actual schedule. So if I round all the weights to powers of 2, that only affects the objective function by a constant factor. Okay. So during our dynamic program, we have to round all the weights to powers of 16. It so happens. So we lose another 16 square there, and then another 8, and so on and so forth. The multi-cut problem that I defined on trees, we don't know what is the integrality gap of that linear program. So it's possible that this LP has constant integrality gap. Similarly, we don't know a true constant factor approximation for the multi-cut problem on trees, for demand multi-cut problem on trees. And this is a natural problem because it generalizes the well-known multi-cut problem for trees. And of course, one major open problem is I just talked about one machine, but what can you say about, let's say I have 2 machines, okay, and even when all the weights are 1. So can you give a constant approximation there? One point I did not write, which is like when I say smaller constant, it's possible that you can even get a p-tas here. So even that is not known. Okay. Right. Thanks. That is even harder. If you don't allow preemption, then there are strong lower bounds, I think. Yeah, then this becomes very difficult. Yeah. For online, yeah. So online, essentially, we now so that's a good question. We don't. So the best known results are log p, log w. And the hardness we know is like a super constant, but I don't exactly remember what's the exact hardness. Okay, but that's also for only deterministic algorithms, I think.
And you also need to assume that time is continuous.
That's less of an issue because at least for the offline problems, you can round everything to integers. So even for online, yeah. So because there are a finite number of jobs, I don't think that becomes an issue. Yeah.